All right. Well, while we're waiting, here's a few news articles you might like. This lets you gain remote code execution on a Microsoft product called Remote Desktop Gateway. So it's pretty cute. It's, I think, one that Microsoft recently patched. They called it Bluegate. And anyway, I was not aware of Remote Desktop Gateway, but it's something you deploy Microsoft products, a software product, I think, but it has a vulnerability. And this is what usually happens. If you report a vulnerability, you typically want to have a proof of concept to at least show the customer to prove that you got it. There is a vigorous debate about whether you should really release proofs of concept. The more technical people really think you should because we can't have any fun with it or practice it or test it out. The more square-suited administrative types usually say, oh, no, don't tell anybody because the bad guys will use it. And it totally is true that a lot of malware uses Heasman proof of concept code. So there's arguments on both sides. Microsoft is at it again. If you use Office 365, they're going to change the search engine in Chrome to Bing without telling you. And Microsoft does this over and over again. Now, their argument this time is better than usual. If you're using Office 365, they want to make the search in the browser search through your Office documents. And of course, that can only happen if you make it Bing. But it seems like they ought to at least tell you. Microsoft has done nasty things like this many times. I think the most evil one was about 3 years ago. They wanted everyone to use Windows 10, so they pop up a box saying, do you want to upgrade to Windows 10, yes or no? And if you click no, it would just do it anyway. Which is the kind of stuff that, you know, big professional companies like Microsoft are not supposed to be doing stuff like that. That's malware companies. But Microsoft gets so vigorous with their marketing that they slip over the edge now and then. So this medical devices are outrageously insecure. The I Am the Cavalry project is a bunch of people working together to secure them. That's because Joshua Corman, who wanted to start a union of security professionals, essentially, like the AMA. The doctors get good laws because the American Medical Association takes money from the doctors and they pay for lobbyists to take Congress people out to parties and write the laws for them and, you know, basically bribe them into doing the law, which is how the American system works. And information security does not have anybody like that, so they keep passing laws that are quite hostile to us. And another less cynical way to describe it is that this stuff is complicated and they can't understand it. And we don't have experts there that can wear the right clothes and go to the right parties and explain it in their language. And so he wanted to do that. So he tried to go to legislators with information about security, and they said, I can't understand any of this, and I don't care because no voter can understand it either, so nothing's going to do me any good. And he said, well, what would you care about? They said, well, hospital equipment that's killing people. From that we could understand, and the voters could understand that. So he focused on that. And of course, as you would imagine, when security experts started looking at it, the stuff is god-awful. And for the last several years, they've been finding huge vulnerabilities in all this hospital equipment because it was designed by people who were trying to make it medically safe, so it would actually solve the problem and not kill the patient, and like clean so it doesn't have germs in it. And nobody thought about cybersecurity in addition to all that. So it tends to just have ridiculous vulnerabilities. Like the most common thing here, it just has hard-coded, unchangeable credentials because, you know, nobody worried about that. And this has been true of pacemakers and lots of other devices. So now they have patches. You know, a lot of these things don't even have the ability to put on a patch and such. You know, it's this is what happens. Same problem with the Internet of Things. If you have gadgets that are designed without any thought towards security, you often have a huge problem. I got in trouble years ago when I informed a guy that had 100,000 websites that his company had made all vulnerable to SQL injection. And I knew he was going to resist like he did because he didn't even have a version number or any kind of update process. He has no way to fix the problem. You know, if you just write software one by one and you tell your employees to just copy this code and ship it out, you don't include any update mechanism because you haven't thought of that. Now you're really in deep trouble if you need to put out an update. So, you know, anyway, so the 4PIX botnet has been around for years, and somebody is removing it and telling people to put on antivirus. And no one knows exactly what's happening, but what's assumed is that some other rival botnet gang has taken over the botnet. This happens a lot, and sometimes they will just replace their malware with my malware, and sometimes they'll fight for control. And sometimes somebody that is like a Robin Hood sort will take over and then try to fix the problem, and that looks like what's happening here. But this happens a lot. So an enormous amount of Windows machines are under hostile control all the time, and the modern the old model was to try to put on antivirus and firewalls and stop it and get it all gone. Now people have pretty much realized that's impossible, and they've adopted the zero trust model. Just assume that some of your machines are infected and have other layers of security to protect them, because it's not possible. There's nothing you can buy that will really stop all the users from clicking on stuff and catch all the stuff they'll click on, and on you go. So this will be an interesting world. Right now, I know a lot of people in security consulting that tell me they pay the ransom all the time. It turns out you get infected with ransomware. Even if you have a backup solution, using the backup solution is so much time lost and so much expense that it would be cheaper to just pay the ransom. So they typically just pay the ransom. But of course, that means they'll just do it again. And so now they're thinking of passing a law prohibiting the government from paying the ransom. Somebody has to stop paying the ransom at some point, I would think. Anyway, it's an interesting issue. I think the US federal government has a policy of not paying ransom to people who kidnap American citizens and hold them hostage. And I think France does not. And so I think they claim that French people get kidnapped more than Americans for that reason. I'm not sure, but this is a hotbed of contention. There are some people say you should never pay the ransom, let those people die, because for every one of those you pay for, there'll be 10 more tomorrow. Other people say, you heartless bum, you have to save the one in front of you and not have some hypothetical economic analysis pretending you're saving these imaginary people later. There's some truth on both sides. Anyway, 23andMe is declining. This is the DNA testing company. They've been laying off their staff. I'm very glad to see this. DNA testing is a terrible idea. Don't do it, because they will just throw the data on the ground or hand it to the cops or let people hack it. So now you have compromised the privacy of you and all your relatives forever. And they are catching people because some relative put their DNA up there. This stuff is wide open to all kinds of people. It shouldn't be. And you can never take it down again. And my parents would tell me never to do this because they lived through the days of Sacco and Vanzetti and the bad times every now and then. And right now, I think it's probably more easy for people to see than the US government could easily decide to ban a religion or something and hunt you on concentration camps and kill you. We are not very far from that. And I think people now can see that more clearly. So they could decide that people with certain DNA markers are the ones that are going to get AIDS, or the ones that are going to vote for the other party or something. We have to round them up, and you'll wish you hadn't published your DNA on the web. Anyway, so this is, Goldman Sachs is going to require diverse boards, at least one woman on the board, or they won't take your company public. And after a few more years, 2 women on the board, or people of color. This is the harsh leftist democratic quota system of reversing discrimination. And I used to be very much against it. I used to believe that things should be a meritocracy. You should take the best people, and you shouldn't be promoting people who didn't score high. But then I became a teacher and I got students jobs. And especially when I started teaching hacking, which is basically cheating, I have to admit that our tests don't really seem to measure anything of any importance at all. I have students who flunk everything, go off and are famously successful, students who get A's in everything and they're useless on the job. And so it is not really true that my test measures your value, and taking the people above 90 and rejecting people below 90 is the right way to get the best people. And I watch, anyway, so this is another alternative. And the evidence seems to be on this side. People have said all along, even strict quotas to diversify things make them better. Because they see there's a ton of people who are not white males who are very good. And the only reason they're not there is because of bigotry. It's not because they're worse. And in practice, that seems to be true. Anyway, so supposedly the Crown Prince of Saudi Arabia hacked Jeff Bezos, but the evidence is not as clear as it should be. They ought to have real known malware with a known MD5, or real connections to a command and control server, or real measurements of data leaving and going to the Saudi Arabians, and they don't have any of that. All they have is the total amount of outgoing bytes per week or something. And he wasn't sending very many bytes out. And then after this date, he's sending more bytes out. So that proves he's hacked it. It proves this one guy did it. And that's not very good proof. And so, but the UN is endorsing it. And so here's Arada Rob, who is a famous skeptic for these things. And he's just saying what I think any of us that play with phones could tell you. Your phone sends data all over the place, lots of data for weird, no apparent reasons. And he's saying, if you see a pattern of data like this, that does not prove you got hacked here and it's stealing your stuff. It's not that simple at all. Anyway, so many people are saying the evidence isn't that strong, but it might have happened. Google tried to put an anti-tracking feature, but they did it by creating a unique signature for every website so you can track you by that. So they kind of undid the entire benefit of the thing they were supposedly accomplishing. Anyway, let's, now we're up to the official time. So we're here at 1:27. And See, I got a few people online and a chat message. That chat message says, DNA testing, I've done it and decided not to publish the results. Yeah, that's true, but the problem is they have the results and they're just putting in an unprotected Amazon bucket and they're just handing it off to cops without telling you. And they're trading it with other companies without telling you and stuff like that. That's the problem.
Well, in order to use it, you have to sign off saying that it's now their property. They can do whatever they want.
Yep, and they do, of course, do all. And the fact is, even if they promise to keep it private, we know companies are just putting stuff on open buckets and losing it. It's, you know, in practice, I mean, I would like to say you get it done with your doctor and it's kept with your medical records and they really try to preserve that stuff. That might be okay. Like you are taking some drug and they actually have some reason for DNA testing would help them give you the right dosage of the drug or something. But anyway, yeah, it's a lot of people have done it for fun, but there is a significant breach of privacy. So I recommend not doing it casually. Anyway, so we're down to Stack Overflows on Linux, and this is where we start doing the real binary stuff. The hands-on projects may not be up to this unless you're getting ahead, but I want to start you getting used to the binary stuff because students tend to have an allergic reaction to binary and assembly code and the debugger, and so we ought to start off gentle. So we're going to talk about how memory is used by C, and then do have information disclosure vulnerabilities, and then we'll work up to a standard buffer overflow. And all this is getting us to the technique published by Aleph Null in FRAC in 1996, which was a known underground black hat technique. And Aleph Null was the first person that wrote a tutorial that was relatively clear and easy to understand. And that started the modern world of exploit development because it explained to people how you actually did this thing of taking a crash and turning it into remote control. And that helped us all understand the principle. And the reason we do this really old stuff is because they all are based on this principle. They're all variations on this theme. So this is the simplest memory corruption attack. So I've been putting all this stuff in the Google Cloud on a Debian server. So I got it here, and let me make my font bigger. If I configure font size, largest. Okay, I think I'll make it even bigger yet. There we are. All right, that should be pretty good. So I've just set up a bunch of these things right before class. Let's clear. Come on, listen to me. There we are. All right, this is a Debian server, and if you look at the projects, these are the command injection projects that do not do it at this binary level. If you look at the first one of these, it tells you how to set up your machine. I was unable to do this, put this stuff in the cloud until I learned this awesome stuff. You can make 32-bit code on a 64-bit server in Linux, which I did not know, and it turns out to be this easy. You install GCC multilib, and now you can make 32-bit code. Now, of course, 32-bit code is for the older operating systems, but it's where you start. And I used to give people a 32-bit VM, which they had to run to do the 32-bit part of this class, and now I don't have to anymore. Now we can totally study 32-bit code on a 64-bit system, which is nice. And we will, of course, do 32 and 64, but when you do it the first time, you just want to make it as simple as possible. So I've got a very simple C program here, and let's take a look at it. Okay, so there it is, ch2a.c, so I'll just cat it. Okay, so all this does is import the standard input-output libraries, and then it makes an array with 5 numbers, 1, 2, 3, 4, 5, and then it tries to print array element 5. And as I've complained about before, array element 5 is off the end of the array, because the array actually is numbered from 0 to 4. So this, if you were using Visual Basic or Python, it would not do this. It would not let you do this, but C is really a very thin window onto assembly code. C just takes each line, turns it into assembly, and does no further thinking. So this reserves room to store 5 numbers, puts them in a row, and calls array a pointer to the first one. And whenever you refer to it from then on, if you do this array bracket 5, it takes the pointer to the first one and moves forward by 5 words. And then shows you whatever's there, and it does not go back and try to decide if that really was part of array or not. It doesn't put some marker at the end of array. Whenever you refer to array plus 5, it just takes the value of the pointer to array and moves it forward by 5, and that's it. So it just lets you point to area that you did not initialize. So I compiled this. I'm going to do it again, actually, because I didn't do it as well as I could have. There. This is the coolest way to compile this stuff. And what's going on here, GCC is, of course, the compiler, and the -O is the output file. This -M32 is what tells it to make 32-bit code, even though I'm on a 64-bit system. And -G tells it to keep symbols. So I can refer to the source code from inside the debugger, which is going to help us today. We're not going to do assembly language debugging today, but source code debugging, which is the easier way where we don't really have to read assembly today. C is good enough to do what we're doing. So that compiles it. And now if I run that, it prints out this strange number, minus 531 million or 5,318,000 or something, which is not 1, 2, 3, 4, or 5. Now, if you want to understand why, you use a debugger. Now, there are a bunch of fancy debuggers, but I'm just going to use plain old GDB, which is the simple command line debugger available everywhere. People say it's hard to use. If you Google it, there's no tutorial that doesn't take 50 pages and teach you 100 commands, but we only need to know about 4 of the commands in here. And you can do simplification of 4 commands is all you use there. It can do all kinds of fancy stuff, but I don't care. So GDB, and I make it quiet here to get rid of an irritating banner, ch2a. That opens it in a debugger. Now, all a debugger does is launch a Python framework. Well, not a lot of them are Python. I don't know if this one is. And then it starts the program and it loads it and then pauses right at the start. What it's doing is loading the program in memory, and it's replacing 1 byte of instruction with CC. CC is a break command, and a break command stops execution and sends an interrupt, which goes to the debugger, which catches it. So right now it has loaded the program and stopped. If I do list, it shows me my source code, and there's my source code. Now, the interesting thing here is when it does this print, I'm finding something strange in that array. So I'm going to put a break on line 5, and then I'm going to run up to line 5. So it ran, and then it hit the breakpoint, and now it stopped before executing this command. So it has now created the array and put these numbers in it, and then stopped. So now if I want to see what's going on, I do info registers. This is my #1 command I do after almost everything in GDB. The registers are the hard-coded registers we talked about last time in the processor. So here's EAX, C, D, and B out of order for some ungodly reason. Here's ESP and EBP that determine the size of the stack frame. The current stack frame goes from 690 to 6B8. And those are all the local variables used by this program. And here's the instruction pointer, which points to somewhere in the main routine, which is not my problem right now. I'm really just interested in the stack. So I'm going to examine 10 hexadecimal words starting at ESP. And this is the thing we're going to do. There's a pattern of commands we're going to use for this entire class. Put a breakpoint, run to the breakpoint, info registers, examine the stack. Because we're constantly going to be looking at what's really in RAM and then doing things to mess it up and seeing what we've done. So here is the stack. And so in the stack, I've got a null pointer here. I've got an address here. Notice the real code is up around 56. So this is some pointer to some real code address. And here are some numbers that look familiar. 1, 2, 3, 4, 5. So apparently an integer is 32 bits. And these are the 5 integers that I defined. Now, after that, this is some other pointer to some other number used by some other purpose. This is not an integer I defined, but that's what got printed out. That FFFF thing is that large negative number, which if I continue, it's going to print this number, minus 10,544, and that's what it made out of this. That's some large negative number. So what's happened is I reserved space for 5 variables, and I put 5 variables, and then I printed something off the end. So this is called an information disclosure vulnerability. I see something that I was not supposed to see. That's a relatively minor vulnerability, but it does show a problem in memory handling, and a more organized language like C would not, or like Visual Basic or Go would not let you do this. You wouldn't be able to refer to things off the end of it. So let me find the mute so these people don't annoy each other. All right, so I think that's all I wanted to make with that one, and I've got a series of other ones moving forward towards the punchline here. Okay, that's information disclosure. All right, and you just see that number there, and I'm not really worrying about what that number is. It's just some number that was used for some other purpose, which I shouldn't have been trying to print. So now let's make a DOS attack. This is chapter 2b, cat chapter 2b.c. Okay, so now I make an array of 5, and then I set the 1000th element to 1. So I go way off the end of it and try to assign data there. So this is writing to the wrong part of memory. Now, if I run this one, it runs without crashing. So I'm going to change it because see, what happened is I think I accidentally compiled it as 64-bit and had a different answer. I think I have to go to 2000 to make it crash. So let's try that. If I go 2000 off the end, and now I compile it with all this junk, there it is. This is 2B. Okay, and now, whoa, I put it in CHBA. I wanted to put it in CH2B. There, just to keep myself under control, CH2B, and it also runs. How annoying. Well, we're going to crash another one later. I'm going to try it again. There's a reason why this is so hard to see. Let's go to 20,000. That'll probably make it crash. And then we'll look at it in the debugger and understand why. So that's 2B. Okay, now it crashes. So I finally did something that was forbidden. Now, segmentation fault means I moved outside the allowed memory range, and that's what we want to see in GDB. So let's look at this one in CH2B, and now list. Oops, I said list. Okay, so here we are. I'm going to define the array. This is the point where something is evil and it crashes, so I'm going to break in line 5 again. So it'll stop before executing line 5, but do everything up to that point when I run it. Now I'm back where I was. Now I can look at what we got here. If I do info registers, I see that the stack goes from A8, 6A8 to 6C8. If I examine some of that, then I go from XA8 to XC8. So this is, in fact, the whole stack frame right here. And I do nothing much here. That's the end of the stack frame. And then I'm writing to some value way beyond this. So I've gone way beyond the limit of where I should have stored memory. And to tell where it crashed, I do info proc map. This shows me the memory segments. And the stack is up here at FFD6. So that is here. Here's the stack. And the entire stack is 21,000 hexadecimal in size. So I'm right now, all my variables in this area, D6E8. And I'm not going to have an error until I go all the way off the end of the stack up to FE000. That's why it took so much. And exactly how far you have to go to hit the end of the memory segment depends on your compiler and the architecture of your machine and so on. So that's why it was many more bytes than I expected it to be. It's kind of random. But this, by the way, is a DOS attack, and this is one that is not exploitable. You cannot turn this into remote control. If you just write until you hit the end of the memory segment and then get an error, this does not mean I can somehow take control of the EIP. It's just a DOS attack that can't be further exploited as far as anybody knows. And that's what most of them are. Most DOS attacks cannot be turned into remote control. You have to have ones that do something more interesting than just hit the limit. This is just like filling up a bucket until it's full. All right, so let's move on to another one. All right, now I guess I can just do this. Let's cat ch2c.c. Okay, so this one, I define it, and now I'm going to write every 100 and go up to 2000. I'm going to keep writing a 1 on all these locations until I can see it crash. Now, when I tried it earlier, it crashed with only 2000. I played with it a bit. Let's see if that's still working. 2C. Yeah, now it's working. It seems to be a little different every time you do it. But now I can see this is a more clear way to see where it's going. So I'll just modify it. And I know that 20,000 is enough. So let's just make this 20,000. All right. And then compile it. All right, 2C and 2C, and then run it. And there it goes. So I can see where it goes. You can see it's going FEEB. So apparently EB was the end of this memory segment. And when it tried to write past EB, that was the end of it. So you see what's happening here. It's just a way to understand what happened. Typically, memory segments end on some kind of even number. So apparently this memory segment went up to EB. All right. So we talked about that. All right. So now let's exploit the stack a little more carefully. Now, the way the stack works, it goes from ESP is the top of the stack, EBP is the bottom of the current stack frame. And in that stack frame, you have ESP here and you have data stored, like a 1 here and something there. You push things on the stack. When you pop things, they'll come off the stack. And the EBP is used to refer to values on the stack. So to refer to a local variable like my I or my array, it will often be referred to in assembler as EBP plus a value, so many bytes from the bottom of the stack. You can also calculate from ESP, but EBP is more commonly used because it typically stays fixed all during the processing of your subroutine. So the point of the stack, though, is to have functions call functions call functions. That's what it's designed for. So when you call a function, it has to stop processing instructions in the original function, then save the current state of that function, then transfer control to the subroutine, then process those instructions, then exit. Now it has to restore the saved state and pick up where it left off. That's the process that the stack is designed for, and that's the process we're going to exploit. So after you call a function, you now have a stack frame with local variables in it that's used only temporarily while you're in the function. And when you return, that stuff is all freed, and you hopefully resume execution where you took off. So when a function is called, it pushes the arguments onto the stack and then calls the function, which puts the return address on the stack. And then, so the return address of where you resume execution is stored on the stack. And that's the game here. So I'm going to play with this one, and this is going to be the next one, which is cat ch2d. Okay, so here I have a function which just makes the array with 5 variables. It has 2 parameters, a and b, but it doesn't use them. And then I call that function with a and b set to 1 and 2, and then I just print that I came back alive. So this doesn't do anything except go in a subroutine, make some variables, and come back. But the point is so we can watch how the stack handles this. So if I run it, of course, ch2d, it's just going to say returned. Now I'm going to compile it again because I don't remember if I compiled it as 32 or 64-bit code. Oh, let's fix that. If you don't know what you've got, you use file. File, ch2d. This file is awesome. It's even been ported to Windows. File will tell you what a file is. It has a whole list of headers and footers and tricks it uses. So it's very nice. And so it tells me this is a 32-bit ELF executable. ELF is executable link format. That is what Linux programs use. Windows uses PE, portable executable. So I did compile it 32-bit. That's what I wanted to know. And not stripped means it does have source code connected to it. It has symbols connected to it. So you can do source code debugging. Professional software and malware almost always has the symbols stripped off, both to make it harder to analyze and just to make it smaller. But occasionally you do get malware where the bad guy left the source code connected, which is pretty nice, makes it easier to analyze. Anyway, so if I run this, ch2d, it just says returned. So it's no fun to just run it. Let's put it in the debugger and then list. By the way, you don't need to type commands out. Just enough to make them unique is enough, and you can use tab completion to finish them. So list will show me that, and by default, list only shows you 10 lines of code. If I wanted to see the whole thing, I'd do list 115. That'll give me the whole thing. So what I'd like to do is run it, and I want to put a breakpoint in line 10, and then a breakpoint in line 5. So it'll pause here, and then pause again there, and I can see what happens. So break 10 and break 5. All right, now I'm going to run it, and it's going to make it into the main routine and pause here. So now if I do info registers, my ESP and EBP are like this. Now I'm going to open up a text document to make some notes in. All right, so in main, ESP is 6B0, and EBP is 6B8. All right, so not very much of a stack for the main routine. Then I'm going to continue. Now I'm in the function. So if I do info registers in function, ESP is 680, and EBP is 6A0. So you can see the stack grows up to lower memory. I had a stack frame here, and then I wanted to preserve that, so I pushed up here and put a stack frame on top of it. So if I want them to be lined up the way they actually are in memory, it would be this way. And that's the last in, first out. I start with the operating system down here, then I push frames onto it, launch the program, then I push frames onto a subroutine, then they call and call and call, and then I start returning, and when I'm all done, I return from this one, and it return back to the operating system. The reason why we're going to do buffer overflows in subroutines throughout this class is something I learned from Georgia Weidman's book. If you try to do buffer overflows from main back to the operating system, they are very complicated because that step is complicated and different. To get a classic buffer overflow, you want this one. You want to exploit this return from a function back to main. That obeys the simple policy. I was driving myself nuts for a long time. I write these codes, buffer overflows, and I couldn't control the machine with them. And until I learned that. Anyway, so that's what's going on here, just so you can see the stack frames and how they're used. And now that we're in here, remember that one actually defined some variables, I think. Oh, no, I don't think it did. I think it defined variables but didn't use them. So I don't think there's anything interesting to see on the stack. Let's take a look. ESP. Yeah, not much of anything interesting. I think we put a 1 in there is all. Nothing too important in the stack for us to do here. So let's just continue. Now I made it and it printed returned. Now I might not be able to view the stack now. It might tell me that it's over. Yeah, so if I want to see it come back, I'd have to add another breakpoint. Let's do list 115 again. And let's put a breakpoint at line 11, or maybe line 12 would do too. Before it tries to return back to the operating system, I want it to break again. So now I run, and I'm in the main routine. So if I do info registers, the stack goes from B0 to B8. So that's matching my storage here. Now if I continue, it goes into here, into the function. And when I examine the registers, it's now from 680 to 6A0, which is different than what oh, that's up here, 680, 6A0, good, okay. And now I continue, it returns to go back to the main program, and now I'm back to 6B0 to 6B8. So it had to restore back to the original condition, and that's what happens in this routine where there is no overflow and things are working correctly. Now, the next one is got up here, cat ch2e.c. Now we finally have a buffer overflow. In main, we're going to call user input and then return. User input is going to define a 30-character text array and then read from the user with getS and then print that buffer. And getS is one of the 10 or so famously vulnerable C functions you should never use, because it has the flaw that it reads from user input without any measure of how long it is. So there's no way to limit how much data comes in. But in the way C is designed, you always have to limit the amount of data because you had to define how big this was and you don't want to go past it. So I run it anyway, so that I've made that already, and that is ch2e. So if I run ch2e, it's asking me for something. I say hello, and it prints hello and comes back. So everything's fine. But if I copy that, and I put in something longer, then it crashes. It still printed it though, which means it stuck it in memory, and then it was able to use that memory, which went way beyond what was allocated, because the way C works is you point to the start of a string and it takes all the characters until it hits a null byte and calls that the string. So it was able to use it even though it was going way beyond where it should have gone. It wasn't until it tried to return to the main program that it crashed. Simply writing past the end of a string does not cause a crash. This can lead to a ton of interesting problems. Anyway, so let's look at that in GDB. So now I do my list again. Okay, and this is where it defines the variable. This is where the buffer overflow happens. So I would like to examine the situation memory before and after the buffer overflow. So I'm going to break at 6 and break at 7. And all right, so now let's run. And now I'm in user input. It went to main, it called user input, and it stopped. Now it's ready to read something in. So let's do info registers. And so the stack goes from 680 to 6A8. So I can just use this, I guess. Okay, so there's my stack frame. Now let's look at that stack frame. X, say 30X, ESP. The stack frame goes from 680 to 6A8, and what that means, 680 is here, 6A is here. Now this is where you begin to get a headache. It is little endian. So the actual byte called 6A0 is there. This is 6A1, 2, and 3. This is 6A4, 5, 6, 7. This is 6A8, 9AB, and this is 6AC, D, E, F, just to give you a headache. And furthermore, when this tells you that EBP is 6A8, it doesn't mean the byte 6A8. It means the 32-bit word starting at 6A8. So the end of the stack is here. That is the stack frame. And this is something we're going to do constantly through this class. You put a breakpoint, you do info registers to find the stack, and then you highlight the stack with the mouse. This is the best way not to go mad. That is where the stack is. And this 6A8 means these are zeros, 4, 8, and C means that whole word starting with 8. So this is on the stack, and this is the next word past the stack frame. And that is called the return pointer. Remember, 56 points to code. That is the code to return to right there. And these are the local variables which we haven't initialized yet. So now it was asking me for input. If I continue, it's going to ask me for input. Now the traditional input to put in is AAAA. This is what buffer overflow people have been doing all along. I've even got a hat for this. AAAA is just by convention handy input. The reason you put it in is because a capital A is 41 in hexadecimal. A little a is 61, we could have used that, but by convention, we use a capital A because when I started computing back in the 70s, there were only capital letters. Small letters are fanciness added later, and a lot of this stuff dates from way back there. So I put in that, and the reason I put that on there is now when I examine the stack, you can find it. There it is, 4141, and here's the other, 4141. Remember, now it fills in right to left, so this is other things. This is the start of that string. Here's 2 bytes of it, and here's 2 more bytes of it, and then you go. Now the stack goes from 680 to 6A8. So this is the stack frame. So right now, nothing has overflowed. I put in 4 characters, it stored them on the stack. It has not messed with the return pointer. So if I continue, it prints out those 4 characters just fine. So I'm gonna put that in the clipboard and run it again. And now I'm going to continue from here because I don't need to see the empty stack. I want to do this. Put in a lot of A's. And now I want to look at the stack under these conditions. And now, whoops, that's not what I wanted. I wanted to examine the stack. I wanted this one. There we are. Now the stack goes from ESP to EBP, which is 6A8. So that's to there. So I can see I put in a lot of A's, but I haven't hit the return pointer yet. So that was not enough A's to make the overflow. So if I continue, it's going to work and exit normally. So I need something longer. I'm going to put that in the clipboard and run it again and continue. And then put in 2 of those. That'll probably do it. And now examine the stack. Okay, now 6A0, 680 to 6A8 ends here. And now you can see I have clobbered EBP with 41, 41, 41, 41. Now if I continue, it's going to crash. This message here is unnecessarily confusing. This means it's stopped with that in the EIP. It's not very clear. If you want to see it for sure, you do info registers. And now you can see that EIP is 41, 41, 41, 41. By the way, EBX is also 41, 41, 41, and so is EBP. This is the difference between a non-exploitable and an exploitable crash. Yeah?
So basically, this is 41, 41, 41. It has no idea where to go next.
Yes. Well, no, it knows where to go. 41, 41 is a perfectly fine address, but it's not allowed for this program. The program is only allowed to use memory that's been reserved for its purpose. Now, I don't, in fact, have physical memory at that address, but you can do info proc mapping to see what memory you're allowed to use. And I'm only allowed to use memory in these segments. So I can use some memory in 56 and some in F7, but 41 is not allowed. It's not reserved for use by this program. That's what it means by segmentation faults. You have gone outside the allowed segment for code. And so it's not that, in this respect, it's not different than the one I had earlier where we ran off the end. The reason why it's different is because when I examine, so what you do to test a program, you throw fuzz at it until it crashes, and then you use a debugger to look at the registers when it crashed. Now, if all you did was run off the end, you'll just see normal values in the registers, except one of them will be hitting the end of something. But if you were able to feed in strings, that's why you always feed in strings full of A's when you're testing. This typical thing you do. There are exceptions, but this is normally what you do. Because then you just do this, info registers, and you look for 4141. If you find A's, that means you control that register. Some of those A's I put in ended up in here, so I can control that register. That's what we're going to do. So there are 3 registers under my control now, which is nice. And there are ways to get exploits with all different registers, but the easiest way is to control the EIP directly. And that's what, so some of those A's could be changed into a valid address, like starting with 56, and I could now execute different line of code than the programmer expected me to execute. And that's called return-oriented programming, where you take the code that's already there and execute it out of order. It seems like a very limited attack, but it turns out to be extremely powerful because the more powerful attack, where I actually inject code and run it directly, turned out to be easy to mitigate. So you can almost never get away with that. Return-oriented programming turned out to be difficult to mitigate, so that beginning technique turned out to be the advanced technique also, where you don't add any code, you just reuse the code that's already there. All right, and I think that might be as far as I plan to go on this demonstration today. Let me see what my slides look like. Yeah, so there's the Stack Overflow, and here's, of course, the ASCII, showing you a capital A is 41 and a capital V is 42 in hexadecimal, which is what we're using. Yeah, there we go. And so it'll crash at 4141. So here's all the commands I used. Like I say, GDB has many commands, but this slide here, and these slides are on my web page too. These are all we use. List to see the source code, run to run it, continue to resume execution after you hit a breakpoint, break to put a breakpoint, X to examine memory, X/10X ESP to look at 10 hexadecimal words at the stack pointer. Disassemble will show assembly code. We did not use that today. We'll use it later. And then info registers and info proc mapping. Show you the registers is the main one we use. The proc mapping we use occasionally just to understand where the memory segments are. But normally we don't really have to worry about it for stack overflows. We're using small pieces of memory in the stack. So that's the essence of how you look at memory and how memory should be used and how you abuse it in the simplest case. And all we're going to do for the rest of the class is abuse it in more and more complicated cases, all based on the same basic principle. You feed in garbage and somehow you get some of that garbage to go into a register. So let's try some of these Kahoots. And then I want to talk about some of the projects. So I got some Kahoots here. Is it going to log me out or something? Oh, neat. Looks like it is not logging me out. Neat. Kahoots has a session fixation vulnerability. I've been logged in since like 2 days ago. So if I wanted to be a jerk, I could complain about the security, but I'm not in the mood. And all right, so 127, chapter 2A. Right, there it is, chapter 2. Okay. So theoretically, those will be Kahoots. You can be able to have them here. Okay, let's see how it works. Looks like it's working. Cheesecake. I think Cheesecake, one of them didn't give me their name, but anyway. In another class. All right. I don't know how many we got online. Looks like 9 online and about 6 in the room. There could be a few more, but there's always some Kahoot abstainers. All right. Looks like 9 is the number. All right. So what is %x in a print command like that? That's a format string that tells it what format to print the variable in. %x means it's a hexadecimal number, %d is a decimal number, and we're going to have great fun exploiting formats later. Anyway, all right. What GDB command shows you the current stack frame? Okay, that's it. X20X ESP shows you 20 hexadecimal, by the way, words. I think it's hexadecimal. Anyway, that shows you some bytes on the stack frame. All right. Which command shows C source code? Okay, that's list. All right. Which language causes buffer overflows? It's C that's not intrinsic to the hardware or assembler, because all the assembly code just works on like 1 or 2 words at a time, and it does something. There's no concept of a string. There's no such thing as a length. There's no such thing as a boundary you go past. The assembly language in the hardware doesn't know any of that. C tried to create this concept of a string you put in quotes that you then manipulate, and that concept is poorly implemented, leading to all these problems. Other languages use different manipulations, like Visual Studio, Visual Basic will just resize it as needed, and so will Python. And in Go, they use something called slices to deal with a different problem, which is that modern languages are not 1 byte per character anymore. It's a variable number of bytes per character. So if you reserved 10 bytes, you wouldn't even know how many characters you could put in there if you have languages like Cyrillic and Arabic and Chinese. So it really has to be a whole more abstract data structure you're creating and manipulating to really handle modern strings. But C had this simple ASCII only plan. They thought, oh, it'll be easy. By the way, Pascal, an older language, I think it's older, just did it this way. The first byte was the length of the string, and so you have a 10 here, and the next 10 bytes of the string, that's it. No null pointer, no nothing, and that was fine. Anyway, it's this weird C concept of a string with a terminator that turned out to be a really poor way to do it and led to just no end of problems. So what register contains the bottom of the current frame? That's EBP, extended base pointer. That is the base of the current stack frame. And all local variables should be below that in memory. Well, you take EBP and add something to it to get to them. Anyway, all right. I subtract something, I'm sorry. Anyway, what memory section is easiest to exploit? Okay, obviously the stack. The stack is easy because an address is just right there. So you can easily get EIP. You can overflow the heap also, but you do not get control of the EIP because the heap doesn't contain stored EIP values. You overflow things that are harder to exploit. And normally you can't have any kind of overflow in the text section because self-modifying code is forbidden, although not on the Raspberry Pi. We'll get there. But under on all sane computing platforms since the 80s, they don't let you modify the text section because that's insane. And therefore you can't have a direct overflow there. All right. So what register contains the address of the next instruction? Okay, that's the EIP, the extended instruction pointer. All right, so here we have the winners. OP, that might be real initials, but you might want to give me a better name if you want your points. R. McClory, that looks like a real name. And that's Cheesecake, who won before and I think didn't take his points. But my grader might know, I think my grader might have figured out who Cheesecake is. She's very good at this. She had to have reached to the email and stuff. But anyway, if you want to make sure and get your points, you have to give me a real name. Anyway, you've been here for an hour. Let's take a 10-minute break until 2, so you can stretch your legs. And then I want to demonstrate the SQL injection, which is worth some demonstration because it often confuses people. So I'm going to stop the recording, but I will leave the share going so the remote viewers can still ask questions.